Excellent. So I think in order to keep on schedule, let's start the third talk of this morning. And it's my pleasure to introduce Davide Barbieri from Madrid, Universidad Autónoma de Madrid, who's going to talk about learning group representations in brain's visual cortex. Davide, please.
Yes. Thank you very much for this invitation, and thank you for taking the effort of organizing this conference. So in this talk, I would like to talk about some experimental results on a problem on abstract wavelet analysis that is motivated by neurophysiology. So it's my intention to give sort of a very brief and sketchy introduction to the neurophysiology that is behind the what I'm trying to talk about, and then go to the experimental results, which are basically experimental results on image processing. So let's see. The neurophysiology behaviors that I'm interested to are related to the visual cortex. The visual cortex is the area here on the back. Can you see my pointer?
Yes, we can see
Okay.
your pointer.
Yes,
Thank you. So is the area here on the back of the brain where most of the image processing is performed. The visual cortex is a highly structured area with many sub areas, and I will not absolutely go even close to digging into the structure of the whole visual cortex, but just stuck with a very simplified vision of area V1. Area V1 is the first area of the brain's cortex that receives signals from the retina. Okay, there is a long visual pathway here, but here the first area in the brain's cortex that receives and processes signals from the retina is area V1. So what is the behavior of neurons in area V1? So they receive, they essentially, each neuron is activated depending on the structure of an image on a portion of the image plane. And the behavior of this neuron is very approximately something similar to a scalar product with a function on L2 of R2 if we imagine that the image is a function on L2 of R2. Okay, so this is a very sketchy model, and this is a very there is a strong spherical cow assumption. I don't know if you have ever encountered this image, but it's something that's very common among modelists. Here there is a lot more going on down here, but for the purpose in this talk, the activity of each neuron in the in primary visual cortex is approximately that of a scalar product with a function. And here on the right, we can see actual measurements that have been performed with some sophisticated techniques of electrophysiology that could also identify the shape of this function. These functions are two-dimensional functions depicted in a color scale. So blue is negative and red is positive. Okay, so these are the kind of functions that are associated to the behavior of each cell in primary visual cortex. And these functions are have been identified, parameterized as Gabor functions. These are works date back at least 15 years, the most detailed result, but already in the 80s there have been very precise results on this that could identify these functions as Gaussian Gabor function, and the whole family encountered in a typical visual cortex of a mammal, that can be a cat, or that can be a ferret or a tree shrew, is has more or less, can be parameterized more or less in this way, by a translation, a rotation, a modulation, and a dilation of a Gaussian. Okay, so here two real and imaginary parts are shown. The imaginary part is due to the complex valuedness is due to modulations. They are shown for fixed values of these parameters, and in particular for a non-zero k. Okay, so it is kind of customary in describing this family of cells to consider the modulation parameter and the scale parameter constant. This is another extreme simplification of the cell's behaviors, but it's very common and dates back to the first experiments that could identify the first sketches of the behavior of these cells that were awarded with the Nobel Prize to Hubel and Wiesel for their research in the 60s and 70s. So it's quite common to just stick with a fixed parameter k and a fixed parameter sigma. There is a whole bunch of literature that I don't want to dig into this, but let me just say that k and sigma, that is the number of oscillation under the Gaussian bell, and the size of the Gaussian bell itself, they can, in a certain sense, be considered as constant for a huge family of cells in V1. Okay, so what remains to describe the variability of these cells is a set of translations and rotations. Translations and rotation means that in performing this operation, we are performing the operation of a scalar product of an image against the translations and the rotation of a single function. So this is what is generally called an abstract wavelet transform, or a group wavelet transform. Okay, so in the next couple of slides, I will introduce some notation for those of you who are familiar with this concept. They are not necessary. I would like just to give some context to this. So when we have a group that is formed by as a semi-direct product, that is a semi-direct product of an Rn with a group of automorphisms defined with a composition law like this, we can define a standard representation, unitary representation of this group on the space L2 of Rn in this way, and define a group wavelet transform in this way. Okay, so this group wavelet transform is an abstract, is a generalization of the usual wavelet transform, where Rn is simply R and the automorphism are given by dilations. Okay, and so by standard arguments, it is possible to see that in order to have a frame, or to have that this wavelet transform is invertible, it is necessary and sufficient that a Calderon condition holds. So in general, one can relax the usual hypothesis of having an isometry, which would correspond in the frame terminology a Parseval frame, and have just a frame, and the frame condition is the same that was discussed by Nir before, just in the continuous setting. And so a generalization of the Calderon condition should hold. Okay, so this condition for the group of translations and rotation that I've just mentioned that we want to use for a model of the cells in V1, this causes some kind of a problem because it is well known that with just one orbit of so the family of functions obtained by all x and all theta for a given psi, you cannot obtain a frame of the whole L2 of R2. Okay, because here this integral cannot be bounded essentially. This is not much of a problem if we are interested in image processing in most of the times. Why? Because most of the images we are dealing with are well sampled. Since they are well sampled, most of their Fourier power is concentrated around the origin. So instead of looking for a frame of the whole L2 of R2, one can simply look for a frame of the polylinear space inside a ball, so some band-limited functions. And then at that point, one can find for a given A and B larger than zero and finite a psi such that this function C, which is the Calderon function that we had here for the group of rotation in translation, is in this interval. Okay, and so in this case, at least for the group of rotations and translation, this is not much of a problem. And I will show you in a while some numerical simulations, just to recall that in this setting, the wavelet Fourier transform is the scalar product of a function, the wavelet, the the group wavelet transform, sorry, is a scalar product of a function which in our case represents the image against the rotations and translation of this mother wavelet psi. And the inverse can be simply obtained dividing the measure in the Fourier transform, if you want, by this constant C. This function, which if don't have a Parseval frame, is not a constant, which is called C. And just as I mentioned, one of the pioneers of this kind of analysis for the purpose of image processing is Remco Duits in the Netherlands with his orientation scores, which are just a variation on these schemes. And he has performed a lot of successful image processing on this setting. Okay, so what is the main activity performed by taking the scalar product or the abstract wavelet transform with the translations and rotations of these functions is the extraction of edges and contours. Okay, so this real part is most elicited by an edge, and this imaginary part is more elicited by a contour. You can also, from visually grasp an intuition of the fact that the imaginary part of this wavelet performs a sort of a numerical differentiation here in the horizontal direction and first derivative. And this real part performs something similar to a second derivative, okay? Here you have +1 and -1, and here you have alternating signs with a larger sign in the middle. So it's not surprising that you can obtain from this wavelet analysis some sort of edge detection. So is this the end of the story? Is this the activity of primary visual cortex? Is primary visual cortex simply an edge detector? So end of the story, what is the problem? So the problem is that we don't have exactly this wavelet analysis. There are other experiments that started in the 90s that were able to observe on the visual cortex at the mesoscopic scale something that is not a single cell behavior, but something that is a configuration on the mesoscopic to large scale. So what are these diagrams? These diagrams are activated regions in a visual cortex of a small mammal, a tree shrew. And so the black areas represent cells that were activated by a stimulus that had the horizontal direction. Here you have cells that were activated by stimulus that has this direction. These are cells activated by stimulus with a vertical direction, etc. And they were performed with experiments by simply showing the stimulus and recording with optical techniques the images. And so what is the point? That the visual cortex, from the point of view of translations and rotations, is essentially a bidimensional structure. So the three-dimensional group of parameters that we have used to parameterize the abstract wavelet transform in the visual cortex are encoded on a two-dimensional structure. And this two-dimensional structure does not contain all the parameters. So these images can be recollected in one single image that has been quite popular in the neurophysiology community for a couple of decades, and essentially shows that, and it also has a quite simple structure from the point of view of it's quite easy to reproduce numerically a structure similar to the one here. So what is this this color diagram? It can be interpreted as a portion, two-dimensional portion of the brain's visual cortex, where each color represents the direction of the wavelet associated to the cell on that point. Okay. So what we end up with is not a whole SE2 wavelet transform, not a whole group wavelet transform, but a restriction of a wavelet transform to a subset which has dimension 2. Okay, so despite this, with this information, the cortex, the visual cortex of our visual cortex has the same behavior, shows a good ability to reconstruct the whole image. Okay, so the problem is the visual cortex restricted to this two-dimensional, now with this interpretation of having over each of these points just one function localized there for producing the restricted wavelet transform. Is this able to I mean, is this injective? For example, can we reconstruct the image starting only from this information? Okay, some simple direct spectral analysis would suggest no. I mean, the spectrum of the restricted frame operator is very badly behaved. Okay, is of course not invertible, but also ill-conditioned. However, this let us see in practice. In practice, if we have this image, for example, we can perform the wavelet transform and the inverse wavelet transform, and see that we can recover here. This is actually a projection on the polylinear space, on some polylinear space, but it's not only the zoom quality. Also from my screen, it's very hard to find any difference because this is a well sampled image. Okay, so we have this way of going from an image to an SC2 full on the full group a wavelet transform and going back. So let us see. These are in scale, in the same scale of the image. These are the real and imaginary part of the wavelet that has been used in the next experiments to take the wavelet transform. And this is in the same scale of the image, the shape of the surface restriction that I've used in this experiment to reduce the number of parameters available, okay? So what happens if we try to reconstruct only with available parameters? If we try to reconstruct only with available parameters, we do not obtain good results. Okay, we use the dual window, if you want to call it like that, and we obtain some. I mean, it's not complete rubbish, but it's a kind of unusable reconstruction. However, this reconstruction reminds some, at least to me, some experiments that were made, that were performed some 15 years ago in compressed sensing, where one had, most of you know compressed sensing much better than me. So let me indulge in some details here, but if I say something wrong, please correct me. So this was one of the first experiments that appeared in the original paper by Candes, Romberg, and Tau, where they had an original image. They sampled the Fourier domain with lines to mimic an MRI scan, and then try to reconstruct the full image from these just these Fourier measurement, and they obtained some bad results. They said these are the kind of bad results used in current, probably in 2005, MRI scans. These are the results using compressed sensing, that is minimization of the L1 norm of the gradient. Okay, infinite problems like this, the total variation function is just the L1 norm of the gradient. Okay, so this image C is what motivated me to try to see if we could, if I could do something similar, taking these bad reconstruction from available coefficients as image C. So also in compressed sensing, it's crucial to have enough measurements. Okay, so if we don't have enough measurements, like in this case, even the TV minimization does not provide good results. So it's kind of fine tuning necessary, and a whole bunch of important results to determine which kind of parameter start to allow you to get good results. Okay, like this. These, by the way, are simulations made on these MRI images using the package, the famous L1 Magic package. Okay, so what is, how are the experiment that I'm going to show made? They are made using the differentiable structure of the group of rotations and translations. So the idea is to mimic, exactly, to mimic this procedure, but using as space of measurements in the group, on the group, not the lines of the Fourier domain, but just these surfaces, which, by the way, are commonly called in our physiology community pinwheel surfaces, because they look like pinwheels. So, okay. So in order to mimic a total variation functional, you have to have an idea of what is differentiation in the group. And so differentiation on this Lie group is defined intrinsically in terms of the vector fields of the Lie algebra. And the vector fields of the Lie algebra have this form, and this Lie algebra has a special property, that is that you can obtain this third vector field. Okay, this X and Y, you can think of them as a generator of translations, and this theta as the generator of rotations. And you can get one translation from the commutator of translations and of the other translations with rotations. So this commutation relation allows you to obtain a geodesic metric on the group, which means that you can join every 2 points on the group with an integral curve of just, for example, theta and x. This geodesic metric is what is called the sub-Riemannian structure and motivates the introduction of a sub-Riemannian calculus. And most of you probably have heard about the sub-Laplacian and all these objects in partial differential equation. In this case, simply the sub-Riemannian gradient is the gradient only along these two directions. So not a three-dimensional gradient, but a two-dimensional gradient. Okay. And a question still remains here about the gradient from the fact that we could use a sub-Riemannian structure based on the vectors y and theta, which appear to be almost the same, but they are not. They are not because if we go back to the structure of our mother wavelet and our wavelet analysis, I'm almost finished. Just a few images and I'm almost finished. So essentially, when we put each of these functions on a point of the image by translation and rotate it, okay, the vectors y and x have these directions. Since they have this direction, the vector y is if you put one of these function on an edge, okay, on the exact direction of the edge, the vector y is directed along the edge. If you put this function here in the orthogonal direction of the edge, the scalar product of an edge with this function here is 0. Okay, so we have two different interpretation. We have an interpretation of y being the vector that is along the edges in the wavelet domain, and x is the vector orthogonal to the edges. So since minimization of the total variation functional in the L1 norm of the gradient has as the objective to exploit sparsity. Okay, so sparsity is in images is something that is related to the sparse presence of contours. So the correct direction in this case with this parametrization of total variation functional is this one. And I have just minimized this total variation functional subject to the restriction that I have. I have not included another restriction, which is a whole other story that I will not discuss about, which is a restriction that tells us that these functions are not have an additional property, have an additional restriction, that is they are CR function on the group. This is the SE2 version of the Gabor transform with Gaussian window being an analytic function that Jose Luis has been talking about before. So I have not included this this restriction. So let us see some of the results. Okay, this I've put it just because it's a sample image. Everybody has seen this image several times. So the reconstruction, I hope you can see from zoom quality, the reconstruction is not perfect. There is still some margin to this kind of reconstruction. I'm going to show some other image. But still, it's a relevant improvement. at the moment, there is no theory behind the restriction to these kind of surfaces. So the whole set of parameters that determine all this reconstruction could well be the reason for which these reconstruction that I'm going to show are not perfect. But on the other hand, I could not inspect the set of parameter I could not find by inspection in the set of parameter better parameters. So there could be something more, and this something more could be related to the fact that this function with Gaussian window have some additional property, and this I still don't know. But in this experiment, at least, we can see that even if much is lost, a kind of reconstruction, and to my knowledge, this is the first time these restrictions of the SE2 transform to this reproduction of neurophysiological surfaces have given rise to a reasonable reconstruction. So again, these are not perfect. I hope you can see that many details are lost, but it's kind of a first step. So this was the problem I wanted to discuss, and I hope I did not miss the point too much.
Thank you, Davide. So I thank you on behalf of people present here, and we have time for one or two questions. Few questions. Okay, so if nobody asks, actually, I have a question from my side. So you look at the total variation, right, to optimize with respect to SE2
Yes.
in this case.
Yes.
And you also use the Gaussian window, as you said,
Yes.
to perform the transform. Now, Gaussian window, I guess, might be responsible for getting that smoothing effect, right, that you showed in the pictures. The hairs, right, the hair strands, for instance, were kind of smoothed out the reconstruction.
Actually, I don't think so, because if before the restriction, I mean, if you design the window, the size and the oscillation below the window in such a way that that this the Calderon constant, the Calderon function is does not vary too much, so the frame constant are not too wildly different, you don't see any smoothing effect. You don't see any smoothing effect.
I see.
I guess that the smoothing effect is just, I mean, this algorithm is trying to recover this image from these two. So I guess that is a flow of the total variation. The smoothness is the flow of the total variation function, because it's not sufficiently constrained, and so it minimizes too much.
Right, I see. Okay, let me actually ask another question. So you use the Calderon condition, and then you perform. I mean, you showed the reconstruction formula before, right?
Yes.
That divided by that C of absolute value of psi.
Yes.
So if I
Yes,
understand correctly,
this is not. This is kind of standard. I think that it's. I mean, I don't claim that this is kind of mine.
Right. My question is that dividing by C of psi, does it really mean that? So I guess in this case, what would be the V star, or as a W star W is not a multiple of identity, right? This is not a multiple of an isometry.
No, W
it
star
multiplies
W is
with
not.
C absolute value of psi in kind of frequency domain, right? And that's what you're trying to do.
It's not a multiple of the identity. You have to use in the star, in the synthesis operator, you have to use the dual family.
Right. So this is a possible inverse, right? But that's not the only inverse, I would imagine. No. Is there any hope, or is there any reason to look for different inversion formula? So instead of using this one. beyond
This
that,
is very quick.
right? I see.
This is very, very quick.
Okay.
So I mean, it's for a standard 512 times 512 image. This takes hundredth of a second.
Mm-hmm.
So it's
Okay.
very, very quick.
Yeah, 10 milliseconds. Very good. But questions? Anybody? More questions? If anybody from the audience? Nope. Then Davide, I thank you again.
Thank you.
And to keep it somewhat on time, I propose to switch to the next